will do like yesterday. So the first one is Amir. So I need you to take the microphone and put this so the camera can follow you, and that's it. 3 minutes, I will take the time.
That's okay? Okay, thank you so much. I want to talk about the electromagnetic cascade, which is a phenomenon that can happen basically during the cosmological distance propagation or inside the astrophysical sources. Basically, electromagnetic cascade is a chain interaction of electron pair production and inverse Compton scattering when you have a high energy photon and you have a background photon field. This photon will interact with the background photon field, produce 2 electron positron. This is the electron pair production, and then inverse Compton scattering. This is what is known as the electromagnetic cascade. So the point that I want to make is that actually my question is that what happens at the ultra high energies? Basically, in the poster, I will talk about what happens at the ultra high energies. If there is a possibility of muon production, and when we have muon production, basically we can have neutrino spectrum from the electromagnetic cascade. I will answer this question, and I will show that how much energy will channel to the neutrinos. And basically, this will be a pure leptonic process for the neutrino production inside the astrophysical sources and also during the cosmological distance propagation. Thank you so much. I think the poster will arrive soon. So.
Thank you. So next one is Gonçalves. I don't remember the name, sorry.
Olá. My name is Diego Silva. I will not talk about neutrinos or dark matter. I will instead talk about the flavons. If you don't know what a flavon is, it is just another kind of particle that is hypothetical, we can say. It has never been detected in any experiment. But I'll let you know that flavons could be, for example, the inflaton, could be also the axion, could be many things. But I'll not talk about that. I'll talk about how we could probe flavons on the LHC, not on the sky, in the case of inflaton. So in order to do that, probe the flavons, we need to set some assumptions and some experimental constraints. You can see on that plot. But when we go to the LHC, for example, there's lots of different kind of process. And you can see on those Feynman diagrams that at the end of the chain, the flavon is that little way. At the end of the chain, you could create some new signatures with the same charged particles. And those are kind of rare on the standard model. So we could use that to probe them. So if you have some questions about that, I'm a little nervous, I can't explain right now. But if you can ask there, I'll be there. Thank you.
Thank you. Next one, and Emilse.
Okay, hi everyone. Well, I'm a PhD student at Pontificia Universidad Católica de Rio, and in this work, I will explain a little more about the high-energy atmospheric neutrinos that we can consider with sterile neutrinos, in this case for 3+2 scenario. I had already presented some progress of this work in previous school, but today I will present the final result of the analysis. And the idea basically is study the survival probability of antineutrinos, and that probabilities at those energies at the order of TeV. We can see two resonance for those sterile neutrinos, and especially MSW and parametric resonance for core crossing and mantle crossing trajectories of the neutrinos. And we calculate these probabilities with the Cayley-Hamilton formalism, and then we combine with the data of 1 year of the IceCube data. And also we use the neutron fluxes and variance of this data, and then we perform the load likelihood analysis as a test, as a statistical test. And then we have the limits for this scenario, and we compare with two best fit values from the short baseline experiments. And I will show you in more details in the poster session. Thank you.
Thank you. Next one, Jorge.
Okay, so basically, my name is Jorge Schifferli. I work at the, I'm currently in my master's, cursing my master's degree at Universidad Santa María, Universidad Técnica Federico Santa María. So as you can guess by the title, what I work on is the theoretical side of dark matter models, specifically spin-1 dark matter models. So as you know from the courses on dark matter, you know that there are many candidates for dark matter. One of them is our WIMPs, as you know. But WIMPs is more like a framework in general, not actually one specific theory or a specific model. It's more like a framework in which different models can arise. And this is where my personal work starts. So basically, what we start with, me and my advisors, is on what is called a minimal spin-1 dark matter model. What makes it minimal? What do we mean by minimal? Well, we try to modify as little as possible the structure of the standard model. For example, we start with just one vector dark matter candidate, and we add just two parameters, one being the mass and one being the coupling with the Higgs. So the idea is that this model it's pretty nice, it's simple, but it suffers from problems with unitarity. So it basically has a cutoff in which it stops working. Here is what I'm working right now. Because you see, this model can be described by a Lagrangian, which is divided into the standard model Lagrangian and this new Lagrangian with the dark matter spin-1 vector. But we have realized that if you take the electroweak kinetic term, mu from the standard model, and we add it to the, well, this actually goes with a trace, do you know the deal? And we add it to the new part, gauge-like vector part for this, for our candidate, we can get the sector of a Young-Mills theory under the SO4 algebra, meaning that Young-Mills theory with symmetry breaking can be perfectly a ultraviolet completion for this simplistic model. Yep. We're finished? Yes. Okay. So basically, that's the whole idea. You can ask me more on the poster. Thank you.
Thanks. We move to the next one, that is Luis Ramos. Luis? No. With Lucas Ramos, sorry.
Hello, test. Okay. Hello, everyone. My name is Lucas. I'm a PhD student at the University of São Paulo, and I'm trying to present here a bit of my poster of a work done with Andrea Lessa from UFABC and Jan from Washington University. So the starting point is kind of the same as Jorge. We want like minimality. So the starting point is the minimal quark-philic T-channel dark matter model, in which you have a mediator Y, a dark matter X, and they're coupled together with a right-handed quark. So the idea is that if X is lighter than Y, then it's a natural dark matter candidate, as it is a Majorana fermion, which is a singlet under the standard model symmetries. Y will have the same quantum numbers under the standard model as a right-handed quark, and then both X and Y are stabilized under a Z2. So this is the only coupling that you can write for them, except for a coupling of Y with the Higgs that won't really matter for the phenomenology. And usually this abundance of this kind of T-channel models is set by co-annihilations involving X and Y. So when the mass splitting between X and Y goes to 0, co-annihilations become very efficient, and you always underproduce dark matter. But if this coupling lambda, which is a trilinear coupling, becomes small enough, what actually happens is that you departure from chemical equilibrium during the freeze-out, and co-annihilations aren't as efficient anymore. Actually, they're never efficient throughout the whole freeze-out process. So what we really set the abundance is a conversion process between X and Y involving other standard model fields, including as Y needs to be colored, for example, a quark and a gluon outside states. So this will open up a lot of parameter space, with X being able to be as heavy as 40 eV. That was, in the co-annihilation scenario, not able to reproduce the radical abundance. And then we can set some bounds on this kind of models by the decay of the mediator at the LHC, since the preferred parameter space actually encompasses this mediator to have lifetimes between a meter and a few millimeters. And there is a gap in soft and slightly displaced searches at the LHC that is very hard to come through. But we also showed that with a very small modification on the signal regions that they have considered on previous searches at Atlas, you can actually improve a lot on the constraints we have on this kind of models, and point out that even for very minimal models, you need to be careful about the assumptions you're making to be sure that you're probing the whole parameter space allowed. So please see the poster for more information.
Thank you. Next one, Murillo.
Hello, everyone. My name is Murillo Silva. I'm a master's student at Instituto de Física de São Carlos da Universidade de São Paulo, under supervision of Professor Ion Viana. The title of my work is Dark Matter Spike and Gamma Ray Boost Around the Black Hole at the Galactic Center. So let's start with the Galactic Center. Well, in 2003 to 2005, I guess, HASS Observatory got this signal of flux of gamma rays per energy, and it still has no mechanism that quite explains it well. So, well, they try to explain it with a power law with an exponential cutoff at around 10 TeV, but it's not quite this, we can see. And this signal is coinciding with the position of the central source, the supermassive black hole Sagittarius A star. And what do we have? when a black hole collapses in a dark matter distribution. Well, Graciela showed us a few benchmarks of dark matter density distribution in a galaxy, but when the black hole collapses, it may form a spike in density, and this may enhance the expected gamma ray flux coming from the annihilation of dark matter into gamma rays. This occurs through, it may say, a portal, but I call it a primary channel. That is the first particles that come from dark matter into the standard model, and they may go through a hadronization process originating gamma rays. Well, then my work is try to explain the source using this expected flux of gamma rays. Then previous analysis said that it doesn't work, it gives a horrible fit, but you may enhance the quality by inserting, let's say, a power law coming from the CFZ, the diffuse emission from the galactic center. You may use the branching ratio, saying the dark matter annihilates not into one, but in various primary channels. And that's it. Thank you for your attention. I'll be glad to explain a little bit more in the poster session.
Thank you. And last one for today, Pedro.
Okay, so hi everyone, I'm Pedro. I'm a PhD student here at University of São Paulo, and what I'll bring here today for the poster session, it's a statistical study on the significance of reactor neutrino signal. So whenever we want to see an excess of some signal over a background, we must be sure that this comes from a signal, not from a fluctuation of our background. And to attack this issue, we do a hypothesis test to see if we are seeing only the background, or if we are seeing the background plus the signal. And to do that, we use some statistics, and more usually the significance of our signal. That's the Z. It's a normal distributed thing. And I wanted to apply this into the context of a known-off approach, a known-off experiment. But we have two data sets, one with a controlled sample, only the background samples. The source of the signal is off, and the other data is composed by the background plus the signal that we want to measure. So we have three ingredients: the number of events that we see in the two data samples, and a scale factor of these two data sets. And it's a problem because we want to calculate the significance of our signal. But this problem was solved 40 years ago by Lee and Ma, two astrophysicists in the context of gamma ray astronomy, and revisited by Cousins 15 years ago. And I explored these two approaches in my poster and applied this in the context of the Coney experiment, as you heard from Eliana yesterday and by Pedro today. That's a reactor neutrino experiment here in Brazil, and the experiment is located 30 meters away from the nuclear core. And I presented there the significance study of this experiment based on the last results published like 2 months ago in March. I don't know how many months ago. And so if you like to see these results and the promising future prospects, please step by my poster and I will be glad to show you. Thank you.
Thanks, Pedro. And now we are finished. So we have 7 posters. As yesterday, we will visit them during the coffee break, and then we will need more time, so we will do during the last part of the day. Now we will break for lunch, come back at 2. At 2, we have the colloquium that will be given by Pedro. He will talk about Dune, the neutrinos again, and the colloquium is part of the school, so all the institute can come, but it's part of the school, so you should be here. If you did not sign the present list of the morning, please do it, and the afternoon before the colloquium, you will have the one for the afternoon. Have a good lunch. Today is normal lunch, so you have a QR code over there, so if you want to go to another place than just to change, check their places. There's a nearby here, very cheap buffet, I think you can go there.